Hello, now I'm going to discuss about the magnitude comparator. For that, first of all, I have taken example where we are going to compare the two numbers which having only one bit. So A is the one number and B is the another numbers. So now we have total two bits are there. So with the help of two bits, what are the possible combinations are there that we have taken here. So 00011011. Now if we compare here, first output we are taking for the when we have both number as the 0. So when both bit is 0 means this is condition what? Both bits are same. So here it will satisfy A equal to B and remaining are 0. Similarly, if you see that again, when we have A as the 0, B as the 1. So now here it satisfies the condition which one? B is greater than 1. That is A is lesser than B. So remaining are 0. So at a time, only one condition will satisfy. Either A equal to B, A less than B, or A greater than B. So when we are comparing two bits, any one condition will satisfy at a time. Next combination we have, that is the combination with 1 0 here. So A is 1, B is 0. So it will satisfy A greater than B. So remaining are 0. Last one we have, both are 1 1. So again, since both A and B are 1, so it will satisfy A equal to B and remaining are 0. So now if you observe clearly here, even if you are not going to do the K map, if you observe the truth table for this section where we have A equal to B, then it satisfies the condition of which gate? Can you see here? If you compare A and B as the input and A equal to B, then this combination is the truth table of which logic gates? So here if you see that both inputs are same, then output is 1. Otherwise, output is 0. So it satisfies the XNOR gate. So this is the truth table of XNOR logic gates. So that's why the expression for A equal to B, this is going to be satisfied by the A XNOR B. Since here A and B are the inputs and XNOR you know that we can write as AB plus A dash B dash. Similarly, if you see that second is A less than B. So it is the condition only one time when A is less than B. That combination we have A dash B. So whenever A is less, that is the A dash B. That means its complement shows the 0 and without complement it shows 1. Next what we have? A greater than B. So when A is greater than B, this is the condition here. So what we have here? A is 1, B is 0. So this is what? A, B dash. So this concept we need to keep in mind that we are going to use later when we'll discuss magnitude comparator with the help of algorithm. So here you are seeing that we have only one bit magnitude comparator we are going to compare here. That's why if you see that you have combinations are less in the truth table. But when we are more numbers are going to increase, like suppose for example, now we have 2 bits magnitude comparators. So in case of 2 bits magnitude comparator, if you see that, so total each number having 2 bits. So total how many we are going to get here? Total 4 bits are there. So 4 bits means to the power 4 is what? 16. So total 16 combinations we are going to get here. And likewise, if numbers are going to increase further, so these numbers are will be more. So that means we'll not able to write completely in a one page. It will go maybe 1 or 2 pages. So in that case, algorithm is going to work. That we'll see later. Now here we have 2 bits magnitude comparators. So In this case, if you see that each number having two bits, A having two bits, that is represented here by A0, A1. A0 is the LSB bit, A1 is the MSB bit. Similarly, in case of B, again B0 is the LSB bit and B1 is the MSB bits. So now whatever 16 possible combinations are there, that those combinations are written here. Now we'll see one by one here. So whenever you are going to compare these two bits, we have to take as the one number, and next two bits we have to take as the one numbers. So here if you see that both are 0 0 here and then here also 0 0. So that binary equivalent is what? 0. So that means this is what? A equal to B, and A less than B, A greater than B, both are here 0. Next, if you see that A is binary, the decimal is 0, and for B, binary is 1 here, that is 0, 1. So in decimal, it is going to be 1. So from here, what you are getting that A is less than B. So remaining are the 0. Similarly here, A is 0, B is 1, 0, that is the 2. So that means again, A is less than B. Similarly, again in this condition, A is 0, B is 3, 1, 1 binary, that is the 3 here. So finally again, A is less than B, remaining are 0. If you see again for the next combination here, we have A is 0, 1, that is 1, this is the 0, 0. So here what you see, A is greater than B. So remaining are 0. Similarly, here if you see that 0, 1, 0, 1, both are equal. So it will come A equal to B, remaining are the 0. Here again, this is the 0, 1, 1, 0. So which one is greater? B is greater and A is less. So this is the A is less than B is 1, remaining are 0. Now again the condition A is 1, B is 3. So it satisfies that A less than B and remaining are the 0. Similarly, we have another combinations. In that, if you see again, A is 1, 0, that is 2. This is the 0, 0. So it's satisfied A greater than B and remaining in the 0. Again, A is 2, B is 1. So it's satisfied A greater than B. So remaining are 0. Again, A is 2, B is also 2. So finally, it is satisfying A equal to B, and remaining are going to be 0, 0. So that we have to check when it is equal, when it is the greater or less than. Again here A is 2, B is 3. So it is satisfied that A less than B. Remaining are the 0. Like this next truth table again we can write for the another combination also. So here A is 3 and B is 0. So finally which is satisfying? A greater than B. Remaining are 0. Again A is 3, B is 1. So it's satisfied A greater than B and remaining are 0. Again A is 3, B is 2, 1, 0 binding is 2. So that means A is greater than B. So satisfied remaining are 0. Last one, both are 1, 1. So that is the 3, 3. So it's satisfied A equal to B and remaining are 0. Now on the basis of this, we can go for the K map. From that K map, whatever Boolean function we'll get, that Boolean function we can implement with the help of logic gates. So now suppose first one, here we have four variables. So 16 square boxes are taken for the K map. First we are looking for A equal to B, and remaining already you know about this K map. So when A is equal to B, that whenever in this column we have 1, for that mean term we'll write 1 in the K map. So here it is the 1. So what is the condition? 0, 0, 0. So this is the 1 here. Again we have 1 here. So it is looking for 0, 1, 0, 1. So this one here. Again if you see here, again we have 1, 0, 1, 0. So 1, 0, 1, 0 is coming here. and last one is 1 1. So that will again going to come here. So here you see that it is coming all at the diagonal elements. So any combinations are not possible. So here all are isolated. Okay. So finally for each one we need to write the product term we'll get here. So for this, if you see that if you write, we'll write here A1 dash, A0 dash, B1 dash, B0 dash. Similarly, for this, we'll get the literals here. That is the A1 dash and A0. And here again, this side we have B1 dash, B0. Similarly, for this, we have A1, A0, B1, B0. And finally, for this last one, we have A1, A0 dash, and again this side B1, B0 dash. So sum of all four is here that represent the A equal to B. In this, whatever common terms are there, we can take the common and we'll try to simplify this. So generally, when it is A equal to B, it should come as the X naught function. So finally, if you see that at last, if you try to simplify this, we'll have A equal to B, in which we'll get here like x1 into x naught, where x1 and x naught is the x naught function, x1 is the A1, x naught B1, and x naught is the A naught, x naught, B naught. Once we simplify, you'll get the situation like this. Similarly, we have to go for the K map when we have A less than B. So again, wherever we have value is 1, that we are going to write in this case also. So for that purpose, again, if you see 1 is here, 0, 0, 0, 1. 0, 0, 0, 1, it is 1 here. Next, we have 0, 0, 1, 0. For that also we have 1. So this one. Again, we have 0, 0, 1, 1. For that, again, we have 1. Finally, again here, 0, 1, 1, 0. 0, 1, 1, 0, we have 1. Again, this is 0, 1, 1, 1. 0, 1, 1, 1 is 1. And again, at last here, we have 1, 0, 1, 1. So 1, 0, 1, 1 is 1. So now here, we can receive that 3, 2, 5, 6 ones are there, so that we are placed. Now, whatever possible combinations are there, we'll make here. So this is the one quad we are able to get here. So row wise common is what here? See, it is the A1 dash, and column wise common is what here? B1. Now another combination here, this two pair is possible. So these two will make the pair. For that equivalent row wise common is A1 dash, A0 dash, and here column wise we have B0. And one more terms, if you see that it is not covered. So again, here we can make that symmetricity pair. This and this we can take. So finally, we'll have row wise common here. What is the row wise common? For this, this is the A0 dash. And column wise, what we have? B1, B0. So finally, again, if you try to simplify this, then we'll get A less than B equal to, for that we are going to get in this case A1 dash B1 plus X1 A naught dash B naught. This is the expression for A less than B, where what is X1, X naught we have written here. Similarly, if we go for this third K map, that will be A greater than B. Again, we have to simplify the function by writing all mean terms, whatever mean terms are given here, like 0, 1, 0, 0, 0, 1, 0, 0. For that, this term we are going to get as the 1. And remaining other terms, again, we have to simplify here. For that purpose, if you'll see in this situation. So next, what we have, first one we have written 0, 1, 0, 0. This one we have completed. Next, what we have 1, 0, 0, 0. 1, 0, 0, 0. So this is again 1. So this one completed. Again, we have 1, 0, 0, 1. 1, 0, 0, 1. This is the one. Next, again, here we have 1, 1, 0, 0. 1, 1, 0, 0 is 1 again. 1, 1, 0, 1 is 1. And 1, 1, 1, 0 is the 1. So again, we have to make the one quad we are going to get here, and another one pair we are going to get here. Again, for this symmetricity, again, one more combination of pair will make. So after simplification, when we have A greater than B, we should have expression A1, B1 dash plus X1, A0, B0 dash. So finally, in this, if you see that to represent the A equal to B, we required here two XNOR gates are required, and for A less than B, two AND gates, one OR gate is required, and A greater than B, we require two AND gates and one OR gates. So already X0, X1, whatever is required here, like X1 is required, that we are going to implement in A equal to B. So like this, we are going to perform the 2 bits magnitude comparators for the two numbers, each number having 2 bits. Thank